So just to start, a little bit about me. I'm Petr. I look terrible on pictures. That's the best one I can find. I'm an engineer at heart. I spent about 20 years in tech, and I'm also a big product and data geek. And most recently, founder of company Synq, where we built data observability solutions. Before that, I was in 3 different companies, mainly scale-ups, where I was running technology. And they have one thing in common, that the data was a very important part of the business. So in one case, it's fintech, another one, market research, another kind of AI application in banking compliance. And in all of them, we had to build quite complex data systems. And to start, I just want to reiterate how we typically design these systems, where in all of these companies, we were ingesting a lot of source data. So we had to build a lot of integrations, land it somewhere in our system, typically kind of very write-heavy storage systems, and then build a bunch of ETL systems to put it into more read-optimized mode, build APIs, and eventually our user-facing app. Now, one thing which is interesting here is that the data kind of traverses through multiple different storages. So on one side, it could be something like Amazon S3 for the cold storage, and then we land somewhere in Postgres, Redis, Elasticsearch, etc. And it rarely stays that simple. And actually, in companies I've seen, it's a very common case that you don't have just that, but you also add data warehousing, which means that suddenly data is kind of going through your company left and right, and you spending quite a lot of engineering power to just build storage systems, ETLs, and move data around. And so this becomes quite difficult because what you have to do is you have to maintain a lot of specialized storage systems, you have to maintain a lot of ETL, and to me, from the engineering perspective, this means a lot of boilerplate. So about a year ago, when we started Synq, we thought about it in a very similar way as we've heard before. Small startup, just a few engineers. How can we build this system differently so we don't have to maintain all of this complexity? And before I dive in how we did this, just a little bit about Synq. We are also observability solution, but we're focused on data ecosystems. So we don't do tracing as you would see in software. We're very much focused on monitoring data platforms. So in that sense, we typically sit on top of a couple of components across data ecosystem, from ETL orchestration to data warehouses, DBT, cloud, and core, which is nowadays very popular transformation framework used by data teams. We also ingest data from code repositories and BI tools. And if you look at all that, we're basically looking at the entire analytics data ecosystem across companies, ingesting logs, metrics, lineage data, in some case directly, in other case we extract it. And then we help them with 4 different things, and very much again agree with previous presentation that for us it was very important we make this very actionable. So we focus on these 4 pillars: help customers detect errors, help to figure out who should own the mitigation. Next one, help them understand, is this error something important, or is this something I can maybe leave for later? And finally, give them all the data they need to resolve that issue. So in that sense, we're helping them route the right errors in front of the right people and then solve it. Typical customer here is a larger company, so 15, 20 people working in data analytics, and at that point distributed across companies, so it becomes a little bit complicated. And so when we were starting the company, we basically thought a lot about how can we spend the most time possible on things which are unique to us as a business, and spend the least amount of time possible on things which, at least from our perspective, are a bit of a boilerplate. So from that side, I always look at it as there are 3 key pieces which we want to spend our energy on. We want to be building new integrations because that means we can work with the wider market. We want to do more processing, which means that we can extract useful things from data. So things like parsing column level lineage, or doing machine learning to detect anomalies in data, that kind of stuff, which is, let's say, specific to us as a company. And of course, we want to spend a lot of time in building the end user application where we deliver the actual experience to our customers. And so the question was if we can do something like this. I'm missing a little bit of gray boxes, but the idea here was, can we find more unified data storage where we can put the data, which we integrate as soon as possible, and then use it to basically power internal data use cases, our in-app analytics, and pretty much all of our interface. And so when we kind of tried to think of what kind of solution we need, we went first back and looked at it from the perspective of what would such storage have to do so we can have almost like all these things combined. And we heard a little bit from Chris in the beginning that ClickHouse is very good at basically all of these things. So from the perspective, what we were looking for is a scalable ingest. So that means we want to throw data in and don't worry about pre-buffering it or doing additional pre-processing, because we want to keep our application very simple. We also wanted to have as flexible processing power as possible, which means that as soon as the data is in, we can transform it inside of the platform without pulling it in and out, and again, paying the price of the boilerplate code. And finally, to be able to do low latency reads. In our case, it doesn't mean like sub-milliseconds, but more so from perspective of, can we serve this analytics into our end users and have the application be kind of reasonably fast. So we settled on somewhere around 100 milliseconds. And of course, being able to do fairly complex queries. And so we looked at the market. We evaluated a bunch of different solutions. There are some obvious solutions we ruled out. So you can't run user-facing application from S3, or Elasticsearch was, at least from my experience, really hard to ingest large volumes of data. So we ruled out some of these storages very quickly. And the ones we looked at more seriously were Snowflake and BigQuery, because these large data warehouses are very good at processing, very scalable ingest, but we just couldn't get the performance we needed into this kind of sub-second region. So in the end, we discarded them. And the last one we looked at before we settled on the final solution is this solution called Timescale DB, which is extension to Postgres, which was pretty good. But when we started to do some irregular ingests in terms of ingesting data today and some data 30 days ago, we realized there were some patterns where it started to be a bit tricky. And I'm sure we can build some of the functionality we have on top of these storages, but we probably would have to optimize them quite a lot. So we were thinking of, is there anything what can do all of this? And since we're on a ClickHouse meetup, you, I guess, know what's going to appear in the middle. But in the end, we chose ClickHouse. And there were a couple of additional bonus points which really resonated with us as engineers, where on one side, it runs locally, which is super helpful if I want to run unit tests on local machine or on CI. It's very, very resilient. We didn't manage to break our cluster in a year, which is very good, and like it's important part of our product. And so far, cost efficient in a way that we are throwing any data we get, and it works reasonably well. So in the next section, what does it then mean? How do we actually go forward when we decided that we use ClickHouse? And the way how we thought about it is basically all that stuff we didn't want to do. Let's see if ClickHouse can do as much of it as possible. So we're going to architecturally thought about, let's draw this box and see, can we throw as much of stuff as we do into that box? And under the hood, we build our system as microservices. We're quite strong on the principle of asynchronous communication, which means that you can think of our system as many services talking to different queues, and eventually each one being responsible for its own storage. And the data-heavy ones look sort of like this, where you basically have a component which is reading a queue, which is called subscriber. which is immediately dropping data into ClickHouse. So we do, again, that's the part where we just don't want to do too much processing, get it into a table. And then we use what I would call the ClickHouse superpower, which is the materialized views, which are helping us to take this raw data landing to ClickHouse into various different formats, which are then very optimized for queries we need to do from our application. So in that sense, you can think of it as we land data to ClickHouse, create a couple of different formats, expose them as APIs, and that's what our front end can use. More practically, this was, I think, the first table we created. We call it runs, which is basically a log record of something what arrives from customer. There's a lot of different details I skipped, but the important ones were, for example, this choice of the table engine. We use an engine called the replacing merge tree, which means that it's the extension of the standard merge tree, but it's helping us to basically deduplicate the table. So for example, we have our tenant is workspace. Each log record has ID and timestamp. So in the case where, for example, our queue will deliver the same event twice, the ClickHouse would eventually deduplicate this. It's also very helpful if we want to do some backfill and reprocessing. We basically rerun everything and wait for ClickHouse merge to prune the old records so we don't have to surgically upfront delete them. So it's very, very useful feature. And the way we land data to ClickHouse is relatively simple. It's one thing we were a little bit fighting with in the beginning before we found the right solution, but after discussing with the ClickHouse team, we landed on the async insert, which is basically we take the records as they come, we push them to ClickHouse. ClickHouse is buffering them internally and eventually flushing to disk. We were spend a bit of time finding these two parameters where essentially what we're controlling that we don't want a ClickHouse to sit too long in memory, so we're forcing it to flush data at least once per 10 seconds. And this is very important as well from the perspective of internal storage, which is something we got wrong in the beginning, where when we were flushing data too frequently, ClickHouse was under the hood creating too many files, which was the only time where we managed to get it to timeout. But after tweaking these parameters, we basically keep the table parts, which is the key metric, under control. We also monitor this, so it's from last year, August, we didn't have any issues. And so if I go how we use this in the app, so this is part of our interface where a user can go and, for example, see the log records for particular, we call it data assets. So in our case, we're looking at DBT model. And what is important here is that when we query from the table, we always reflect the columns which we used in the order by key for the table, which means that we're efficiently using ClickHouse index. And we also, this is one other trick we had to do, or we have to found, is that we always limit the data by a key, which means that if we at any point end up with a table which has multiple duplicate records, before the ClickHouse is able to deduplicate them, we also limit it in query time to be sure we never really return two of them. This is where it gets a bit more interesting. So when we thought about powering different, more complex views, this is, for example, part of a view from an app where we display status of assets. So you can think of it as we are observing entire data platform. There might be 5,000 assets, and you ask a question, what's the latest state of all of them? Which ones are okay? Which ones are in the failure mode? And to answer that question, we felt we don't want to query this big logs table, so we transform it into more optimized table. And this is where we use materialized view, where the table will be organized in slightly different way. So it's by workspace. Target is the actual data asset and created at. And the query which we do to fetch this data is again mimicking the structure. So we're using the appropriate ClickHouse index efficiently. Now, under there, I also put in a few statistics where you can see, I think we mentioned the compression rates in ClickHouse, and in the statuses table, because of how we put it into the disk, we are compressing from 72 to 3 gigabytes, which is 25x, which is pretty good, which means that this additional table doesn't cost us much. It's 3 additional gigs on top of another 60. And that means that the performance is on fire. This is a snapshot of data from basically querying these key tables in our system for about a day. And what you can see is that the most common queries are 46, 65, so somewhere in the range of under 100 milliseconds. There are a few slower ones, but it's mainly kind of trade-off of do we want to optimize them. And actually what I'm looking here is not a latency of ClickHouse, is latency of the Go microservice on top. So there is even more kind of overhead, but this is kind of the performance you can feel from the user perspective. I recorded a bit of demo. So this is how the app feels, where I'm looking at the overview of given asset. I might look at the logs, zoom to a specific period of time, open a specific log. So it's really responsive. So the user really doesn't need to see too many spinners. They just go around, find what they need, and get out and do something more interesting. This is lineage. This is doing the query to the status table. So you can look at it as behind the scenes. On each of these screens, we do 3-4 very targeted queries to very optimized tables in ClickHouse and get this very interactive performance so the user doesn't have to wait. But it has limitations. This is something what at least I was bending my head for a while, where we realized that materialized views are very good for most of the use cases we had. But when we started to build this particular view, it didn't work as expected. And the reason for that is this little bar is something what we took from the status pages from software. So what we want to do is, for a given data table for the last 30 days, I want to show what's the status of the table. Was it failing or was it always okay? Which means we want to roll up a lot of data. So for each table, about 30 days of logs. There could be thousands of these tables. And we also want to calculate downtime. So if the table was okay, okay, error, and okay, that diff between these two records, I want to count and I want to sum it up and see what's the total downtime of such table. And so we do this window function where I want to pick up for every record a previous record for that asset. But because of how materialized views work, it didn't really work for us, which means that the previous record is typically not in the batch of new inserted data, so we would miss it, and essentially this query would result in incorrect results. And this is where we kind of thought a little bit about how are we going to solve this, what are different mechanisms, but under the hood, ClickHouse is still able to create such views. But instead of creating materialized views, we do this as create table as select statement. And for that, we brought another tool called DBT. I don't know, are there any users of DBT here? Oh, a few. So DBT is a transformation framework, which is very popular, especially in analytics teams, which is helping them orchestrate fairly large DAGs of data transformations. And so because we support it for our customers, we took that inspiration of using the tool and we essentially use it to orchestrate a sequence of select queries inside of our cluster, which is calculating on schedule and pre-processing data for these views. How does it look in practice? This is our miniature DAG. So in the beginning, I have my logs table, which I then do about 3 layers of transformations where we kind of re-roll the data into specific views. And essentially, we create a couple of tables on the right, and these tables are, again, very hyper-optimized for the queries we do in the interface. And this is one example of DBT model where, on the left-hand side, I'm saying, I want to create a new model as select statement from a table. I want it to be stored again in a replacing merge tree. I'm even choosing my order by key. And when I'm querying this data to the interface, I'm doing this very simple select statement where I just say, select data from this table and apply exactly the same filters as what we used to lay out data on disk. So this is again like a couple tens of milliseconds query. And now that when we thought about this, we realized, well, we now have all this processing power for our application. Well, we can also use this internally. So what we do is we ingest data from other parts of our stack. So all the user tracking data, or also number of important queues in our system. All of this end up in the ClickHouse. We run DBT, calculate some DAC of transformations, create specific tables like health score for the account, and then surface this in BI tools, and eventually use this for our internal analytics. And because we are observability company for data, we actually monitoring our own system with our own system, which means that we're actually ingesting our ClickHouse data, our DBT execution, and data from GitHub, process it, and send these very actionable alerts when things go wrong. So this is two examples of error messages I got over the last few days, where one of them is when ClickHouse decided to kill one of our DBT jobs for good reason, because it was taking too much memory. So in that case, it might have user-facing impact because one of the tables backing our product didn't materialize as it should. So we get notified. This is exactly what our product does for our customers, so we can want to use it in the same way. And then I can look at this and decide, well, is this something user-facing? Do I want to fix it now? There was a PR I did about a day before that, and it has impact on something else. So this is how we're kind of actioning the observability for our data teams. And the second example is from our latest product, where on top of all this, we're also helping companies scan the tables themselves. So for example, when we're ingesting our own data to a cluster, we're monitoring that it's actually arriving. And if there is any deviation from standard pattern, which we learned over the last month of data, we might alert. So in this case, one of our systems wasn't sending data as it should. We detected it in ClickHouse, alerted ourselves, and later realized that there was an issue in our core system. And so to conclude, we basically have what I dreamt of in a way. We have a no boilerplate system where we're really landing all of our data into ClickHouse Cloud. We're spending most of our energy on building integrations, building our kind of business-specific microservices, and building our end-user experience, which is great. By the way, we use a few other storage systems, so we have still Postgres for things like workspace management and a list of users, where that wouldn't really make that much sense to push to ClickHouse. We also use Redis for some specific use cases. But if you look at it from volume perspective, it would be 98% of our data would be sitting comfortably in ClickHouse. And so if I reflect back, why I think ClickHouse is awesome for what we do is that I really look at these three buckets, which we started with, in the perspective of, does it scalably ingest data we need? The answer is yes, it works really well. Does it give us low latency reads? Yes, it does, as we saw in the presentation. And the main thing I'm excited about is this whole flexible processing, because if I think of it from the perspective of a startup where we are still a fairly small team, we want to be able to build new features fast, which means that if, for example, we have idea of, can we build a new view for data which would be useful for end user, because all data is sitting in one storage, we can write SQL, sit with the console for 1 or 2 hours, build a prototype, get it in front of a couple of customers very quickly, in literally a day, and see if that works. If that works well, we put it into materialized view or DBT, orchestrate it in production, and ship it, which means that we have a very fast way to turn these new features. That's all I have. Thanks so much for listening. If you have any questions, I'll be happy to answer.